Hello, my name is Andrew Aples, and today I will be presenting the research I have been conducting with Dr. Sue in the master's program here at Northeastern. My research consists of synthesizing a drug along with developing a method of analytical separation using high-performance liquid chromatography. The drug I am synthesizing is a peptide, the 15 amino acid sequence of the islet neogenesis associated protein, known as INGAP. INGAP has been found to be an initiator of islet neogenesis, which involves beta cells in the pancreas. As we know, it is these beta cells that produce insulin, so you can see that it has the potential to treat diabetes. Nevertheless, its cell signaling pathway is not fully known. I am synthesizing the 15 amino acid sequence of the protein that carries the biological activity. This sequence here, called INGAP-P. It also promotes islet neogenesis. The objectives of my research are synthesize INGAP-P and cyclic analogs, purify peptide by high-performance liquid chromatography and mass spectroscopy analysis. First, let me discuss the synthesis. Peptides are composed of amino acids linked together by an amide or peptide bond. This bond is formed by the reaction of the acid group of one amino acid with the amino group of another amino acid. If these two amino acids were to react, they would form potentially four different dipeptide products. Two products with the same amino acids and other two products inversely sequence. What is needed is a technique of single addition coupling in one direction. Now, solid phase peptide synthesis is such a technique that I've employed in my synthesis. It entails stepwise FMOC protected amino acid addition onto a resin, removal or deprotection of the FMOC group, and then coupling of a new FMOC protected amino acid. Here's a closer look at the stepwise coupling and deprotection procedure. You first start with a solid phase of resin beads. These have a density of free amino groups that will bond with the first amino acid that is FMOC amino protected. It also has protecting groups on its side chains as to hinder possible side reactions. The first coupling is followed by an FMOC removal step in basic conditions. After this, you repeat the coupling and deprotection steps for the consecutive amino acids in the sequence. To verify the coupling and deprotection steps are complete, you test a few beads with the Kaiser test. This test solution turns blue in the presence of amino groups. If there are no amino groups present, no solution color change is observed. And so, you desire a Kaiser test negative after coupling, as this indicates completion and no free amino groups from the previous amino acid, and a Kaiser test positive is desired after deprotection, indicating that all the FMOC has been removed from the last coupled amino acid, readying it for the next coupling. The flow of events for each coupling is thus coupling, Kaiser test, deprotection, Kaiser test. The ease of solid phase peptide synthesis is in the fact that after each coupling and deprotection reaction, unreactive reagents are washed away by vacuum filtration using a glass-fritted peptide vessel. After the last amino acid is coupled, the free amino end is acetylated as to avoid unwanted side reactions. This is how I constructed a linear analog of INGAP. For the cyclic analog, amino acids have been added to the sequence, incorporated into the sequence, that can be selectively deprotected and then coupled together. After this, whether it be the linear or cyclic peptide, the peptide is cleaved from the resin and side chains deprotected in an acidic cleavage cocktail. To date, these are the structures of the peptides I have synthesized, that of the linear and cyclic analog of INGAP. But why synthesize analogs? Potentially, these analogs may have a greater bonding affinity to the receptor that plays a part in islet neogenesis initiation. By manipulating the structure and polarity of the INGAP peptide, it may be possible to get a better hand-in-glove fit with the receptor and thus induce a greater therapeutic effect. I have used multi-mass spectroscopy, preliminary identification of my synthesized analogs amongst the product mixture. This technique ionizes a sample, accelerates these ions through a detector at different rates. The results are indicated in a scan that displays peaks for each product mixture component at a +1 on the mass to charge axis. This is my scan for the linear analog. Its mass calculates to 1700.8 AMU. It is possible that the mass spec was not calibrated properly, so instead of getting a +1, 1701.8, I'm receiving the signal of the molecular weight of the linear analog. These other peaks here, it could be a good assumption that they are just the base structure is, they are derivatives of the linear analog, just they have reacted, side reactions have produced them. Here's the mass spec of the cyclic analog, same thing, probably improper calibration of the instrument. Now it appears at 1682.8 at a fraction, it's not even seen here. It is at a fraction of intensity of the other main peaks. This low yield of cyclized product may be because of ring strain, because of the conformation of the individual amino acid amide bonds and or also steric hindrance. In other words, the linear peptide may be a little too stiff to bend. Now, yet I have found there is at least a small amount of the cyclic peptide in this mixture. Now, while working on synthesis, I have also started developing a method using high-performance liquid chromatography for separating the components of a reaction mixture, whether this mixture is from synthesis or degradation studies. This method will assist me in identifying and quantifying the separated components. Now, HPLC uses a polar mobile phase to carry a sample through a nonpolar stationary column. Attraction of nonpolar areas of sample components to the stationary phase cause it to slow down as it passes through the column. The more nonpolar the component, the more will be retained by the column. Differences in polarity will thus cause the mixture components to leave the column at different times. As the separated components pass the UV detector, its absorbance is registered against time in a chromatogram. Now, one of the first things I'm doing, actually right now, just starting the instrumentation, HPLC instrumentation the past couple months, is I'm testing columns for efficiency and integrity. You got to choose a column out of these, a bunch of these from a drawer. I'm using a purified INGAP peptide as a standard in this testing. An indicator of a utilizable column are the peak width and symmetry of a sample of standard. It is ideal to have a minimal peak width so as not to overlap peaks that may come before or after, such overlap decreasing resolution. Peak symmetry is also another indicator, as a lesser downward or forward slope of a peak may interfere with the resolution between a peak and its neighbors. From the integration report of this column, it has an acceptable peak width, yet symmetry is wanting, exhibiting a lesser downward slope called tailing. The integration report for this column indicated a more adequate peak width and symmetry. It does, though, indicate more of a lesser forward slope, which is called fronting. Here's a chromatogram of a sample of cyclic analog product mixture. All the relative mass spec peaks should have corresponding peaks in the chromatogram. My goal in the research is to eventually match the mass spec peaks to those of chromatogram. It's the cyclic analog chromatogram and its mass spec, which I showed earlier. Like I stated, there's very little cyclic product. See, one of the main peaks seems to be the uncyclized linear product, and it may be good to assume that these other peaks are just reacted, unwantedly reacted linear analog. Now, this slide compares chromatograms of the cyclic analog mixture and the INGAP standard. All method parameters, instrumentation column, etc. are identical. As there is very little cyclic product, let me just see if assumption that the peaks. So notice a clear difference in retention between the INGAP peptide and linear analog cluster. The reason for this may be due to differences in overall polarity between the two. The INGAP peptide has an additional isoleucine nonpolar group. The linear analog has two additional polar groups, the ones that are incorporated for cyclization. And all this equates to the INGAP being more nonpolar and attracted, and thus attained more by the nonpolar stationary phase of this method. Now, the next steps in my research are to continue testing different HPLC parameters as to improve resolution of the peaks of a synthetic product mixture. Also, I wish to fractionize the eluting components from the analytical instrument and then analyze by mass spec. And after this, evaluate possible mechanisms that may be evolving the additional peaks seen in the mass spec and chromatogram.